Okay, students, now we'll talk about chapter number 5, linear momentum and collisions, and you can find that in page 258. We need to remember that we see the first video that talk about the definition of the momentum. The momentum, it is a vector physics quantity that told us how much we need force to stop a moving body. This body, if it has high velocity, it will be difficult to stop it, or if it has high mass, then it needs more force to stop it, because the definition of momentum is the mass multiplied by the velocity. If the velocity gets high, then the momentum gets high. If the mass gets high, then the momentum gets high. If both of them are high, then the momentum is also high. The units of this momentum quantity is kilograms because of mass, and meters per second, and it is a vector quantity because the velocity is a vector quantity. As a magnitude, the momentum is equal to the mass multiplied by the speed with the same units. Let us now start solving some examples for a body. A person with mass 70 kilograms walk with velocity 2 meters per second, say for east, which is the same as x plus direction, or to the right. They are all the same direction, these directions. Okay, we just need to put the numerical values. The mass is 70, the velocity is 2 in east direction, then the total momentum will be 140 kilograms meter per second to east, or we can write it in vector notations, which is 140 x hat kilograms meter per second. This is simple, just put the numbers in the formula. Let us now compare small thing as a bullet and a huge thing as a train. The mass of this bullet is approximately 0.02 kilograms, and its size is just like this. And the velocity for it, it's high. It's high. It's about 1,000 meters per second. It is fast. But the train, which is huge, 5,000 kilograms approximately, and the velocity is slow in general, we assume it 4 meters per second, and both in x direction. We don't care about the direction now, we are talking about the magnitude for small things and big things, small velocities and high velocities. We can easily compute the momentum. It's the same formula, but we need to put each mass and each velocity for those two bodies. The momentum for the bullet is 20 kilograms meter per second, but it is for the train, the mass multiplied by its velocity is 20,000 kilograms. It is slow, but its momentum is high. That's because of its mass. Look at the bullet. It is small in mass, but its velocity is high, so its momentum is something measurable. But what if the velocity is just 4, like the train for the bullet? So the bullet's momentum will be the mass multiplied by the velocity. This will be equal to 0.08 kilograms meter per second. This will be very small. The same way, if we take the velocity high for the train, if we take the velocity is equal to 1,000 meters per second, then the momentum will gets very high also, because the mass is 5,000 and the velocity is 1,000. This will give us 5 millions kilograms meters per second. So the momentum in general depend on the mass and the velocity. Okay, now if we need to compute the change in momentum in one direction, it will be easy. The change in momentum is delta P, which is equal, as we always know, that P final minus P initial. It is the same as delta V is equal V final minus V initial. Delta X is equal to X final minus X initial, and so on. If we have the mass with the same, for the same body, it is the same mass, there is no change in the mass. Have the same, this mass has V initial and then V final. Then this mass will be with momentum P initial, which is M multiplied by V initial, and P final is M multiplied by V final. The change in momentum is P final minus P initial. P final minus P initial. It is easy. Okay, now P final, this value, M V final minus M V initial. The same M, we can take it out of these terms. Then we get V final minus V initial, which is M multiplied by delta V. This is the change in momentum. Okay, let us compute that for two examples. If we have the same body with mass 3 kilograms, V initial is 3, V final is 1. It is slower, yes. So delta P is equal to P final minus P initial. P final is M, V final. M is 3, V final is 1. P initial is M, V initial. We can get outside M from this parenthesis, and we can find that M is 3, V final is 1, V initial is 3. This will equal minus 2. Then the change in momentum is negative 6 kilograms per second. Be careful here. Look, we have P initial is equal to the mass, which is a 3, multiplied by V initial, which is a 3. This will be equal to 9 to positive X direction. Now P final is equal to mass, which is 3, multiplied by V final, which is 1. This will be equal to 3 in positive X direction. Where is the change in momentum? The change in momentum is negative 6. This is delta P, which is equal to negative 6 in X direction. Does that make sense? If you add 3 minus 6, it will give you 9, the initial momentum. Now, if we'll take this example, you will see that in some experiments. Now, if you have a ball with mass half kilogram with initial velocity positive 5 meters per second in positive X direction, as we see, and the final velocity is positive 5 meters per second in negative X direction. It is in this direction. Okay. So we have now V initial is equal to positive 5, V final is equal to negative 5. Because of the direction, we change the signs. Okay. Now delta B is equal to P final minus P initial, which is equal also to the mass multiplied by delta V, which is V final minus V initial, as we see. The mass is half, V final is negative 5, minus V initial is 5. This is equal to minus 10, multiplied by half, which is minus 5 kilograms meter per second. The change in momentum is equal to minus 5. That's mean in negative X direction. We can compute the initial potential. It will be positive 2.5 in X direction. The final potential is negative 2.5 in X direction with a negative sign. You can see here. The change between them is the final value minus the initial value. Minus 2.5 minus 2.5, it will be negative 5 kilograms per second, which is the same value. You can do this way or in this way. Okay. Third, now we will need to talk about the momentum in two directions for many bodies. Okay. It will be easy. We can compute the momentum. We can use the two directions with vectors. and it will be easy. You will see that we have three objects, balls or anything you need to call them: the first mass, the second mass, the third mass, with first velocity, second velocity, third velocity for each one of them, and these are the values for them. First mass, the second mass 3 kilograms, this is half kilogram. The velocity for the first mass is negative 4 meters per second in y direction, in negative y direction. This is in positive y direction in 10 meters per second. For this is negative 1 meter per second. What is the total momentum for this system? We have three balls. For this system, we need to find the total momentum. It's easy. It is easy. The total momentum is simply is the summation of these potential momentums. I'm sorry, I always say potential because the potential energy, sometimes we call it P. Okay, P1 plus P2 plus P3 for the first body, second body, third body. Now P total is equal to M1 V1 for the first body, M2 V2 for the second one, M3 V3 for the third one. Okay, the first mass is 1, its velocity is negative y in y direction. I will use the vector notations here. The second mass is a 3, the velocity is negative 1 in x direction. The third mass is half with velocity 10 meters per second in positive y direction. So this will give us minus 4 y hat, minus 3 x hat for the second body, and the third body is 5 y hat. We just need to combine the components together. This is just one term in x direction, which is negative 3 x hat. 5 negative 4 is just 1 y hat. This is the momentum vector with two components, minus 3 in x hat and 1 in y hat. If I need to draw it, just I take the components. This is minus 3. I take the magnitude 3 centimeters, and I draw 3 centimeters in negative x direction, positive 1 centimeters for the y component for this momentum vector in positive y direction. So this is the x component and this is the y component, and this is the resultant between them. I need to compute the shape. This is py. I need to compute the magnitude of the p total, the resultant momentum vector. Using the Pythagorean theorem, the magnitude of p total is equal to root of px squared plus by squared. Px is negative 3 squared, py is 1 squared, this will be 9, this will be 1, this will all together will be root of 10. Be careful that I use the minus sign here. It is okay. If I need to use the magnitude of this component, which is a 3, it is okay. But when you use negative 3 squared, use them all between parentheses. But because if you use this, maybe you will get it minus 9, because you will forget to take the square for the minus sign, because the minus sign should be squared. When the minus sign squared, it will be positive. So to neglect any mistake in computing the negative sign with any number, just put parentheses. Okay, so square root of 10 is 3.16. This is the magnitude of the total momentum. If I need to find the direction, I need to find phi. Phi using tan inverse for py by v px, which is equal to tan inverse 1 over 3, not minus 3, because I take the magnitude or the length of it, which is 3. This will give me the phi angle, which is 18.4 above the minus x-axis. From here, from the minus x-axis, not from positive. If I need it from positive, it will be 180 minus 18.4. Okay, now we know what is the linear momentum, what is the relation between the momentum and the mass and the velocity. We know how to compute some examples, simple examples. We know how to find the change in momentum. We know how to deal with many objects in 2 dimensions and find any vector property for this momentum quantity. See you in the next section. Thank you.